All right, I guess let's get started. So today we're going to talk about file system verification in a somewhat different style than the CivFS paper that you guys saw last Thursday. So this is the paper on FSCQ, this verified file system. So this is actually the piece of work that mostly got us excited about verification. This is one of the first few things that we actually proved in COC that seemed like a real deal. So one reason why we wanted to sort of look at this paper, generally we have a bit of a bias, I think, against our papers. We don't want to have to present our own work here, and we're biased in that way. But it does seem like an interesting example of sort of system verification, where we're actually proving interesting properties that might actually be worthwhile to formally verify in practice. And the reason that we are excited about file systems in particular, sort of a combination of three factors. I think one is that it's actually a pretty important infrastructure or important code that is widely used. Real systems store their data on a file system. And related to that, the specs are actually pretty stable. So you might imagine that things that don't have stable specifications are hard to verify because the ground shifts underneath you. But this is a pretty good target, I think, for formal verification. Whereas at the same time, there's actually bugs. So despite the specs being actually pretty stable, the implementation keeps changing and bugs keep being discovered and so on. If you remember the first lecture that I gave, we gave some background on file systems and their correctness and bugs. So I think this is one reason why we're excited about file systems as a target for verification. But at the same time, file systems have some unique properties that we haven't really seen verified yet, and in particular, crashes are a big deal for file systems. And long ago at this point, in the first lecture, I talked about logging as a basic technique that gets used to ensure crash safety and make sure that your file system doesn't get corrupted when the computer powers off. And actually, the crash reasoning is going to be the focus of labs 3 and 4. And in lab 3 in particular, you guys are going to implement and prove a simple logging system, like a simplified version of what FSCQ is doing here. And so crashes is one tricky aspect of file system reasoning. Another is non-determinism, somewhat related to crashes. Because crashes can happen at any point, but there's actually an additional non-determinism that FSCQ tries to grapple with, which is this problem of the asynchronous disk. And this actually adds quite a bit of complication to the file system design and to the specs and proof. And the sort of end result is an actual file system that this paper describes that's actually implemented in COC, very much in the style that you guys are doing in the labs, and sort of spec proven and so on. One thing I should say is sort of maybe as a defensive aside, if you will, is this is a bit of an academic paper. A few of you guys had questions. I think the first two papers that we read were from Amazon and Google and Facebook and even CompSearch. These are real things that are used pretty widely in practice. And this FSCQ paper, maybe along with CivFS, are a bit of a phase transition where we're really looking at state-of-the-art verification. Maybe FSCQ not state-of-the-art as of like a couple of years ago now, but still, these are fairly recent results. And as a result, they're not really of the form of being used in industry or these ideas are being deployed. The goal of these prototypes, it's cool, or we're excited about the fact that there's prototypes in there, but the goal is really to show an idea and not so much to have people use FSCQ. We actually put a big disclaimer on our FSCQ GitHub repo saying, please don't use this code, because despite having proven theorems, we don't actually maintain it. So there's all kinds of annoyances and maybe even bugs in our specs in principle. So even though it's proving against a spec that might not be what you expect. So the ideas are demonstrated by FSCQ of some kind, and maybe these will be interesting things for others to build on. And we've built on them ourselves. But it's not really at the level of Amazon's verifying their AWS services of some kind, or even the CompSearch artifact. So it's just sort of the ground rules. And actually, I should say, I think we're entering a phase in this class, in these lectures, where we're going to look more and more at now more state-of-the-art results, as opposed to sort of these broadly used ideas. And many of them are of this shape, where you'll see a prototype described in the paper, and there's some cool result being shown, but it's really rough around the edges. There's some core nugget that's pretty cool, but it's not a production system. And I think the goal here is going to be try to extract interesting ideas or ways of thinking about verification and specs, and not so much trying to evaluate, well, did these guys actually get a product out the door, or is this being used today? All right, so that's sort of some of the context for what we're going to be talking about, this FSCQ paper. Just to sort of explain what this FSCQ artifact looks like, it is very much a thing that looks like the stuff you guys have been doing in your lab assignments. So what's going on here is that the implementation itself, this FSCQ, right, this definition, this stuff is very much like the implementations you've been doing in Lab 1 and in Lab 2, where you write this in Galena and you call some low-level opcodes. In your Lab 1, it's reading and writing variables. In our file system, it's reading and writing from disk. That's basically the only difference. Everything else we do in Galena, very much like the labs do. And then we prove specs. So in Coq as well, write about the same implementation. And these look similar, although not identical to the lab specs. And then, as you can imagine, we have some logic under the covers. So this is basically the CHL, crash core logic, that we use in the paper, is sort of a fancier version of the lab infrastructure. So this crash core logic here defines things like the exec relation, how the system runs, what the sort of structure of the specs are, and so on. And we basically run this theorem. The diagram in the paper shows the Coq proof checker sort of being on the side, but really the Coq proof checker is running and checking this QED statement right here. And if the theorem proves, then according to our model of execution, our file system has some kind of a correctness guarantee. And then the rest of the pipeline, we haven't sort of dwelled on it much in class, but looks like the lab assignments, where we sort of run some extraction commands, and this produces this Haskell code at the bottom, in the middle here, rather, that sort of mirrors the implementation from above. And then we just compile it, and we actually get really an ELF executable at the bottom here that Linux can run. And the cool thing here is that Linux actually has this nice, for development purposes, interface called Fuse. And what Fuse is a way for us to get system calls that go into the Linux kernel. So here's a regular Linux application like MV, a command you might run from your shell. This guy is going to issue regular system calls going down into the kernel. But Fuse is this clever upcall library that lets you sort of redirect these syscalls back up to your user space file system implementation. So traditionally, these file systems sit somewhere in the Linux kernel, written in C, because it's a little bit tricky to get other implementations into the kernel. But with Fuse, we can run our file system implementation as just another process on Linux and use this upcall mechanism to service the system calls. And then our Fuse implementation of the file system is actually going to read and write disk blocks on disk. So read, write this, implement this rename operation, and then return the results all the way back to the application through the same Fuse API. So that's the general flow of things for how this file system works out. Just to sort of maybe set the context and help you guys appreciate what is or is not existing here. So any questions about this, or what's this artifact we're talking about, and so on, before we dive into the sort of spec details and what's tricky? All right, feel free to ask anytime. So let's talk about, well, maybe that's not the slide I wanted. Let's talk about what the goal is. So the goal for us, sort of broadly, is to specify the full file system, but as I mentioned, the particularly challenging thing for a file system has to do with crash safety. And the reason this ends up being tricky is that you might have a computer sort of drawn by this, line running along, you have some executing thread, and then all of a sudden your computer crashes. You lose power, or maybe you have a bug in your OS kernel, which in our case is not verified. Maybe that panics and reboots. And after your computer reboots, you eventually start running again. And the question is, what's going on here? You crashed, you were running along. What can you say about the state of the system after the reboot? And there's many kinds of goals you might have. So you probably want to make sure that your OS can actually boot up. It would be cool if your file system was intact in some form, like you could actually mount your file system. Even sort of better yet is if your user data is still there. Although this gets a little bit trickier. It's like OS boots, yeah, of course, you gotta boot the OS and you gotta be able to mount your file system. The user data being present, not all user data is probably gonna be present because you crashed in the middle of doing something. So maybe something is gonna get lost. For example, the file that you were just writing, or maybe some recently written files, depending on what the spec is. So here, this gets a little bit fuzzier in the sense that we gotta really precisely specify what we should expect in terms of the user data being present on disk or not after we reboot and recover our system here. And the reason this ends up being tricky is the fact that you can actually crash at any time. And this is kind of tricky for developers to reason about because they're typically used of, well, many software developers, I'm sort of oversimplifying here, but typically you think of calling a function and you sort of start running a function, you call it with some arguments, you get some result value, you just sort of think about, well, the result value is good or not, or the function did what you wanted or not. But the crashes can expose all kinds of strange states in the middle of your function that you wouldn't have seen if the function finished to completion. So just to give an example, so here's a fairly standard file system layout that we can imagine. So here maybe we have an inode, which in a Unix style file system represents a file. And inode basically consists of a list of blocks, so pointers to block number. So here maybe we have an inode that points to this particular block. That's the first block of the file. And here's another one. That's what the inode looks like. So the inode data structure is stored in one block, or maybe there's several inodes per block. And then it has pointers to other blocks that actually store the contents of your file one block at a time. And then on the side, you also have, and there's probably many inodes in the file system, but we'll ignore those for now and instead look at the allocator. So allocator is something that keeps track of disk blocks that are not being used by any file right now. And this allocator stores maybe pointers to them in maybe an efficient representation, or in this diagram, just a pointer. But here's an allocator. It's got a couple of disk blocks that it knows about that are not being used. So suppose we wanted to do something like append to a file. So here's some data. You want to write F and some new data. And the file is open in append mode. So what has to happen is we got to grab a block from the allocator, stick it in the inode, and write the data there. And the problem is that there's actually several disk writes involved in this, right? So you got to first find which block you want to use out of the allocator here. And you want to sort of grab it from the allocator and actually put it into the inode. So this means you got to add this arrow going to this block. So we wrote this sort of pointer in the inode. And we probably need to delete it from the allocator so it doesn't get used again. So we're going to kill this link. And then we probably need to actually write the new data into this block itself. So the block contains the new values that the user wanted to write. So you can see already that's basically 3 disk writes. We need to write to the inode to change this pointer. We need to write to the allocator to delete the block from the allocator. And we actually got to write the new data. And as you can imagine, if none of this happened, if you crash and none of these updates went through, you're good. You basically didn't do any damage to the system. And if all these updates went through, then you're in pretty good shape too, because you actually did append to the file, you wrote the new data and so on. But the problem is if you have a subset of these writes that come along, then you might not be in such good shape. So imagine that maybe you wrote the data, so maybe this made it to disk, and this made it to disk, but you crashed before you got a chance to remove the block from the allocator. Now what happens on crash is that your inode is pointing to the block and the allocator is still pointing to the block. So now if your application calls append on a different file, that same block is going to get used for a new file as well. And now you'll have 2 files sharing the same block, which is going to be bad for correctness, among other things. This is one order that doesn't work out so well, but actually most orders also don't work out so well. So for example, if you wrote the allocator block and the inode block, but not the data, then what happens is that the file has a new block and it's not in the allocator, but the contents of the block is garbage. It might be actually the data of some previous user that was using the block. That would also be bad. So the goal for us really is to avoid these problems and reason about what are all the possible things that could go wrong if you crash at any point in the execution. And indeed, people actually get this wrong often enough. And the sort of standard technique that you've probably seen for that I guess described in the first lecture as well, for avoiding this problem is to use logging. So logging is the general plan for getting this sort of atomicity correct. And as a pretty clean solution, it has a few performance problems, but it's pretty widely used. And the story is basically that the rule is you never update in place. So the sort of mental model you should have with logging is that the copy of, if there's one copy of data, it is dangerous to monkey with it by touching it directly, because you might crash in the middle and you might not finish your set of block updates that you're trying to do. So instead with logging, the thing you should really do is always think, first write to the log, and then once you've written to the log, then you apply the log. So the log stores the operations you want to do. And the reason you want to write to the log first and then apply it is that if you crash between, then the recovery code is going to kick in. So when you reboot and you run some kind of a recovery routine, it's also going to apply the log. So even if you crash, someone will finish applying the log for you. And this stuff is tricky to get right. I showed some examples in the first lecture that I'm not going to repeat now, but it is a tricky piece of code to write, especially if you want high performance. Now, admittedly, this file system we're talking about today is not super high performance, but it does exhibit some of the trickiness that you might run into in a logging system. And some of the follow-on work that we did actually tries to push FSCQ towards closer towards the kind of performance that ext4 achieves, at least in terms of sophisticated optimizations. All right, make sense? Questions about this so far? All right, so let's talk about this logging layer. So that's sort of the core contribution of FSCQ, the verified reasoning about a logging implementation. So if you want to verify logging in some sense, there's a couple of things we got to do. First is we got to figure out what is even the spec. How do we capture this notion of being able to write multiple things to disk at the same time to address this problem that I was showing on the previous board? So we'll talk about the way that FSCQ does this. Another thing that turns out to be quite important is how do you model, and here by model I mean modeling the world underneath of FSCQ. In some sense it's just another spec. It's a spec for the disk on top of which FSCQ is running, but it is indeed important to capture the behavior of the disk to the extent that it's important for FSCQ's correctness. And then we got to model what it means for a computer to crash and to recover. So all this requires us to really pin down the details in some formal way. And we'll talk a bit about how to model the disk. And finally, we got to figure out how we're going to structure the proof here. And there's several aspects with proof, as you can imagine. One is that even in the absence of crashes, we got to figure out just sort of functional correctness arguments. So this is almost the same things that we saw last week with SibleFS. So those guys worry about all the correctness of a POSIX file system, and they use their spec to check if a file system happens to work in the cases they were able to test. But in FSCQ's case, we really want a mathematical proof it's going to happen in all the cases. There's some trickiness here to even prove correctness in the absence of crashes. But then we might also even have crashes. So we have to figure out how to, what should the proof structure look like in that situation. Make sense, hopefully? All right, so let's see, what should the spec look like? So there's sort of a nice notion that FSCQ tries to provide in the spec is this notion of a transaction. And transactions are a pretty good idea, comes, I think, largely from the database community, thinking of changes to your system state in terms of these nice units of logical sets of operations that you want to perform. And the properties that we want from the kinds of transactions that FSCQ is going to support in its logging system mostly have to do with atomicity. So atomicity here, I mean in the sense of either all the updates are applied to disk or none of the updates. So when you want to do that kind of file append, which involves 3 disk writes, I want all 3 disk writes to happen at the same time, or none of them. So we'll need to figure out how to capture that notion in our specification. I'll actually talk about the precise way we formulate the spec a little bit later, once we've built up some machinery for talking about crash behavior. The other thing that you might worry about or might want from a spec is durability. So by durability, I mean this question we asked earlier on about what should happen to the user data. So it might be great that your user data is added to the file system in an atomic way. So maybe it's all there, or maybe none of it is there. So the none part is a little bit worrisome. And the none part is basically what the durability part of the spec worries about. The question is, what should you expect to be durable after the computer crashes and restarts? And for us, sort of the question, I guess, yeah, persisting after a crash. In FSCQ's case, the file system actually does the simple and very durable thing. Basically, once a transaction commits, then you should expect it to be around after a reboot, after a crash. This turns out to be not so great for performance because every time you commit a transaction, to make it durable, you got to write to disk. And disks are very slow compared to a CPU. So real file systems actually don't write to disk right away. They sort of wait for a while and see if an application really asks more explicitly using the FSync system call to flush stuff to disk. And we have some follow-on work. There's a pointer in the lecture notes for a file system where we designed that actually has different durability guarantees. So not everything is durable right away. That's good for performance, but interestingly, it actually changes the spec quite a bit because as you can imagine, the spec captures what the expectation should be of the application. So if your spec says you have full durability, then implementing this optimization where you don't flush to disk right away, good for performance, but breaks that durable spec. Some of these decisions about how to formulate your spec are really going to have serious performance implications in terms of what kinds of optimizations you can and cannot play. And the other sort of aspect of a transactional system that this paper basically ignores has to do with concurrency. So one question you might ask is, what if you have multiple transactions running at the same time, many threads running? What happens then? Well, this paper basically, assumes sequential execution. So there are no threads. We have some follow-on papers as well that look at this concurrency angle, but I think to a large degree it's still sort of an open problem how to do concurrency the right way with crashes. So we'll see what the right answer is, but this paper certainly is trying to tackle the problem of a single threaded or a single core file system. All right, so that gives you maybe some sense of what the spec should be for a file system logging layer that everything is built out on. So now let's talk about this modeling question. How do we model the system on top of which FSCQ is running? So to do that, let's look at sort of what a simplified disk model might be. So here's a starting point, maybe. So a simple disk model is you just have an array of disk locations. So it's kind of like a memory, except that this thing sticks around on crash. And the other difference is that each cell is large. So you have these cells, they're numbered 0, 1, 2, up to the size of the disk, some kind of an N. And every one of these guys is a sector. So in file systems, each one of these sort of disk units called a sector or block is typically something like 512 bytes or maybe 4 kilobytes in more modern storage devices. But it's a moderately large compared to a DRAM memory, moderately large unit that you can read and write at a time. And operations that you get on a disk are basically read. So you can read an address, or you can write, and you can write some value to an address. And these are the operations that you actually have already seen in the labs, in Lab 2. And for our purposes, we're also going to talk about sync, so flushing changes to disk. And we'll see why this sync is important in a second. And at least in a simplified sort of synchronous disk model, where there's just readings and writes, things are actually pretty similar to a memory. So if you remember in last lecture, Tej was explaining how you might write separation logic specs for just memory accesses. And the disk operations actually look the same way. So you might imagine a spec that says, if you have an address that points to some value v0, then you could call write on that address and write a different value. And the post condition is that address now points to this new value v. So this is the sort of Hoare logic syntax that the separation logic paper uses for writing little specs like this. So hopefully that makes some sense. The simplified disk model that I've shown here, though, is a little bit too naive. So here's the reality of what a disk system looks like, and I'm sort of even there cherry picking some aspects of reality. But here's what your computer probably looks like: is you got a CPU, and then you have various kinds of system buses. So maybe there's a PCI bus and a SATA bus connected to each other in some way, and maybe a couple of other things. And this thing ultimately connects to some kind of a disk controller, which is basically another CPU inside of your disk, the box that's actually your disk device, and it's got a SATA port or maybe some other kind of a port for newer disk devices. And this thing actually has its own memory. So it's got a DRAM for storing data. And behind the scenes, it's of course connected to, maybe it's connected to a rotational disk that actually stores your stuff on platters, or maybe it's connected to flash chips, which store your data in flash, and so on. But this guy actually orchestrates all the operations. These reads, writes, and syncs that we talked about on the left are actually interpreted by the disk controller. And in reality, for performance, what actually this guy does is it actually maintains some kind of a write buffer with all kinds of writes in its memory. So the rules actually, how this actually works is that when you issue a write to the disk controller, it actually goes into the memory, into this buffer. This is the buffer. And the reason that the disk actually, the reason the disk controller implements the write this way is because it's faster. If it had to write it to rotational platters on the disk or to flash chips, it'll take much more time to do that than placing it in the little memory buffer that the disk controller has. Maybe it's not so little, maybe it's these days like even a gigabyte perhaps on a fancy disk controller. So that's one difference between sort of our nice little model and reality. There's all kinds of memory and real disks, real sort of storage durable devices here. And the problem is that this memory actually might go away in a crash. So if the crash doesn't happen, then things are actually pretty nice. So the read actually goes, first checks the buffer or goes to durable storage if it's not in the buffer. So if it's not in the buffer, there's probably also more stuff going on in memory. There's a cache. But if it's not in memory, the read will actually go to the flash chips or the platters and read it for you. And then there's the sync operation that can actually flush the buffer to durable storage. And the other sort of operations that we might want to talk about is the crash. So what happens on a crash? Actually, in this picture of reality, the crash is in some ways actually maybe simple. So you just lose the memory and the buffer that's stored in there. But this might actually be kind of complicated for the CPU running your file system. So the file system is probably running over here in your OS kernel. Might be kind of annoying for the file system to deal with because it lost some set of writes that it issued recently, in the not so long ago, perhaps. Another thing going on in addition to the crash is there are some background operations. So in the background, while your file system is running on the main CPU, the disk controller could be doing stuff of its own. So it can actually take stuff from the buffer and move it to durable storage, even though no one issued a sync command. So it's allowed to take any set of writes. It doesn't have to be in order, it can be out of order, and actually make them durable. Maybe it sort of plays some optimization game to cluster them together so that writes to nearby addresses are written at once. So that's the story of reality. And this is a little bit more complicated than this nice memory-like model that I showed on the left. So the question that we asked you guys for reading this paper is really trying to figure out, how does FSCQ model this? So how do we reconcile this sort of maybe overly simplified picture I drew on the left and the real disk that we have on the right? So I was hoping to get you guys to go into breakout rooms and chat about this for a little bit. So we'll give you guys 10 minutes or so. Let me assign you to breakout rooms here, and we'll let you chat about this for a bit. So just to remind you, the sort of question we want you guys to mull over is, what's the model? How do we capture all the messiness of the real disk in the model that FSCQ actually uses and describes in the paper? So any questions before we jump into this breakout? Cool. All right. So see you guys in 10 minutes or so. All right. So welcome back, everyone. Yeah. So I wanted to ask, so what do you guys think in terms of the disk model? How does FSCQ actually model all these weird behaviors of reality? Anyone want to jump in and say what your group thought? Maybe I'll pick on some names. So maybe Eileen from your group, what did you guys think was the modeling plan here?
Yeah, basically it seems like for each block you save both the last written value and the previous values. So because of the buffer, you know that after a crash, any of those previous values could end up showing up, not just the last written value.
Yeah, so I think that's right. So basically, the model is sort of extended, so the state looks a bit different. And the model looks kind of different from reality in the sense that in reality, there's a single buffer, but in the model, the buffer gets sort of split up by address. So it doesn't quite look like what the implementation is behind the scenes, but tries to capture this business of losing the buffer on crash. So anyone else from the other group, Julian, maybe? Do you guys think of any other sort of aspects that FSCQ models here?
So I was a little bit confused on this. So if we if we look at the question from, if we're writing blocks B1 and B2, and then a crash happens, and we know B2 is on the disk.
Yeah, so maybe let's go through that. That seems like a good question to try to sort of maybe make this a little bit more concrete. So the question from that we strictly speaking assigned was sort of this execution where we had first write to some address, and then we wrote B1 perhaps, and then we did a write to maybe the same address, and we wrote B2. So then the question is, I guess the question asks what blocks does the disk store, but I think implicitly what that was getting at is, suppose that you now crash, what will read return? What could read return? I think the answer here is that if we look at what really happens, so the write goes into the buffer. So what's going on is actually this B1 and B2 are somewhere in this memory buffer of the disk controller. And if you lose power, this whole thing goes away. So there is no more buffer here. That's gone. And now, if you do a read, the thing that you get back is potentially B0. For all that was like, B0 being the thing that was in block at address 8 before you did any of these writes. So you could even get the value that was there before, or it might be that in the background, because of this rule, while you issued the write, you didn't call sync, so you didn't guarantee that the writes made it to disk, to the durable storage. But in the background, the disk could have been doing that anyway. It doesn't have to wait for your sync. This is without the sync part. So you could also get B2 or B1 even. So the reason you might get B1 is because B1 got flushed here in the background, or perhaps it got flushed here even after the disk got B2, and somehow through some implementation choice of this disk controller, it decided to first write B1. Seems relatively less likely. Maybe you would have gotten B1 more likely because you, sort of the disk wrote it here, and then you issued the B2, and the B2 didn't make it out of the buffer. That makes sense?
I have a question.
Yeah.
So we said that with asynchronous writes, the write could return before it actually writes to disk.
Yeah.
So then how do we know that this post condition of in the paper,
so how do we... What I should say, right, like this is basically for a synchronous disk, which is not reality, or maybe it's like reality if you carefully configure your disk to disable this write buffer. So in some disks, they have an option for you to disable this write buffer and to always go to disk right away, always go to durable storage. That's possible, slow, so many systems don't enable it, most systems don't enable it, and many disks don't even have an option to disable this write buffer. But in principle, it could be possible. So that's how you might establish this post condition. But we'll get to it in a second. So actually, yeah, let's maybe start talking about how FSCQ models this. FSCQ actually captures the model where you have a write buffer and you still have a post condition. And the trick there really has to do with figuring out what the post condition means. When can you really rely on it? So let's talk about that. But sort of before we jump in, does that sort of make sense, or are there sort of more questions about the concrete execution and what you could see on disk or not? That more or less clear? All right, so let's start talking about how FSCQ models this so that we can actually talk about this and still have this sort of nice post condition. So the plan is basically to, in this async disk model, so the plan is we'll still have an array of addresses, one location per block number, but each one of these locations, as you guys were saying earlier, is going to store not just a single block, but actually a list of block values. So it might have store 0 and 10 and 7 and 3. And the meaning of this, so for address, all the addresses are up here still. The meaning of this list of values is that these are the writes that you've performed to the disk since you last flushed. So this guy is going to be the latest. The last element is the latest write you had. And when you read, that's what you'll get. So effectively, this guy in the end of this list is what's actually sitting in the disk controller's memory. That's the last write you made to that address. But all these other guys are also writes that you recently made. And as a result, they're going to help us reason about what might be true on a crash. So the reason we have this model that sort of breaks up the buffer by address is that it's going to simplify our reasoning. Because instead of having to reason about all these writes going into one buffer and then splitting back out and going to individual addresses, we can do per address reasoning with this model and not have to reason about a global buffer where everything sort of jams together and then we got to disentangle them. So let's look at some sort of executions here. So maybe we'll have, let's say, a write to an address A. We write the value 10, and then we're going to read A from that address. And then we'll write some more to that address. We might write 11. And then we might want to talk about, at this point, we'll call sync. And then we can see what happens there and what might happen after a crash. So the way I want to reason about this is I wrote down these system calls, or sort of disk operations, really, that we want to consider. And I want to sort of write almost pre-post conditions. And I'll just sort of intersperse them between these calls. So the post condition of one guy is going to be the precondition of the next guy. Almost think of this as like, a piece of code that you're running that has like 4 statements in it. So we're going to start out with address A. It's going to point to, remember now, things that addresses point to are no longer a single block value, but really sort of a list of things. So maybe suppose we have the value 0 there initially. So when you do a write, what our model says in FSCQ is that you don't actually replace what the address points to, you add on to the list. So after you do this disk write, now A points to the list 0, 10. So 0 is the previous write that you had there, 10 is the new guy. So now the question is, what happens if you do a read? Well, the way you figure out what you're going to get from a read is that it's always the last element in the list. So the return value is going to be equal to the last thing in the list 0, 10. That's sort of, the spec is going to be sort of more general. It's going to be the last of whatever A points to. And also, by the way, we still have the value on disk. It didn't go anywhere. So the read doesn't change it. Does that make sense? So that's how we can sort of model the fact that we have outstanding writes that we haven't flushed yet, but we still, the read is guaranteed to return the latest write if we haven't crashed. So this is sort of where the post condition comes in. We do have a useful post condition for write that captures both the fact that 10 is now the most recent value, and it still keeps around the knowledge about what other values might be either on disk or in memory, like the 0. So this post condition lets us reason about what read should return, because it's always going to be the last thing out of that list, and still preserves information about possible crash outcomes. So just to sort of keep going here, after we write more, this list just keeps growing. There's 0 and 10 and 11. And now this is the point at which we might ask, like, what happens if we crash here? Well, at this point, we haven't synced yet. So we have no real guarantees about what is or is not on disk. So at this point, if we were to crash, before the write, there's only one value. The thing on disk is going to be A sort of points to 0 on disk in some loose syntax. But at this point, we might actually have 3 outcomes, right? It might be that A points to 0, or A might be 10, or A might be 11 after a crash. And the general way to think about this is that after we reboot, so if we were in this state over here and we were to crash and reboot, the computer is going to, according to our model, pick one of the values in this list. So after you crash and restart, you're going to pick that as being the only element of the list, and there are no other pending writes. That make sense? So this is sort of the way that the post condition works for us. So you were previously asking, like, well, the post condition seems overly strong. So indeed, that post condition is indeed too strong. But this clever way of putting the previous writes in your value allow us to make the post condition sort of both accurate and useful. So hopefully that clarifies that a bit. And then after we issue a sync operation, then what happens now is that now we discard everything except for the most recent value. So now A points to 11, and that's the only value that is stored in our model. And that implies that if we were to crash now, then the only possible crash outcome is going to be A is going to be 11. That make sense? Any other questions about this sort of asynchronous model of the disk? So for FSCQ, this is just a set of axioms, if you will, about how the world is going to operate, or about how read, write, and sync are going to operate. We don't actually prove this against any implementation of the disk controller, but we think that this is a sort of an accurate approximation of what the disk controller does. Of course, we might have this model might be overly conservative, right? So if you issued lots of disk writes, not all of them are likely possible at any given moment, but this model is reasonably easy to reason about, rather than something perhaps more sophisticated that you might cook up.
It's not just that it's easy to reason about, it's also captures the fact that we don't really know what the disk controller is doing.
That's right, yeah. So maybe the envelope allowed by this model is broad enough that pretty much every disk should fit according to our understanding of what disks guarantee. Indeed, good point.
Right, and unfortunately, it's difficult to imagine even a model that is less inclusive than this one, that would actually be guaranteed to cover all the disks that we might end up buying.
That's right, yeah. So it might be that there's some funny things that you might, some implementations rely on. So some implementations maybe don't reorder writes, who knows, but, or you might exploit some structure that on a given platter, things don't get reordered, who knows. But indeed, this is a very much, I think, the right sweet spot for how to model a disk compared to exposing any additional details. That, yeah.
It might also be worth pointing out that this general style of model shows up in lots of other contexts as well. For example, in DNS, where updates to DNS are not guaranteed to be distributed everywhere. In fact, DNS doesn't even have a sync operation.
That's right, yeah. So many of the systems, especially in networked distributed system context, you don't really want consistency right away, or for performance reasons, not because you don't like consistency. It's important to model all the different states in which you might be, and then eventually you'll converge either over time or because of an explicit flush or some other event. All right, so that's the way that FSCQ models the disk. FSCQ also introduces a sort of a different way to model crashes in your code. So while you execute, we need a way to model all the possible ways in which we might crash. So the main idea here is to really sort of split the reasoning about crashes into two phases. So the first question that we want to answer in reasoning about code is sort of, where might we crash? And the question where here sort of, in what state might we encounter a power failure? And therefore, what are these states that we got to reason about after we crash? And the second question is, how do you recover? So what happens when you reboot? So you encounter some kind of a state, you crash in a particular state. Now, what's going to happen if you take that state and then you reboot, and then you start recovering and then proceed with booting up your operating system, your file system, and so on. So this first question is answered basically by this notion of a crash condition. And this crash condition is basically an extra post condition. So just to give you an example, so for a simple operation like a disk write, this almost ends up looking kind of trivial. In verification, often at the lowest level, things look trivial, but then they combine in surprising ways, perhaps. So here we maybe have A points to 0, and then we issue a disk write, and write 10 to this address. The post condition is still what I was showing on the left here. You add 10 to the set of possible block values, but then we're also going to add a crash condition to the same specification. And the crash condition almost always is going to be the sort of either the starting point or the sort of return value for simple operations like a disk write. And this sort of captures the fact that when you're doing a disk write, when you crash, you either crash before the write happened or after the write happened. So in disk systems, this is usually called an atomic sector write. And this basically says that one thing that's impossible is you issue a disk write, and during the disk write, you could have crashed in some bizarre state where the value was partially written. So it would be weird if some of the bits of this number 10 or this block 10 made it to disk, but not the whole block made it to disk, only the first half. That would be kind of ridiculous for the way file systems expect to use a disk. And indeed, pretty much every disk out there tries hard to guarantee that writes to one of these sectors, which is 512 bytes or 4 kilobytes, as we were saying, those changes all happen all at once. So there's some unit of atomicity that we can rely on. And these crash conditions allow us to sort of capture exactly at what point we might stop executing. So one thing to note here is that there's this weird thing which says that, well, you crashed in a case where A pointed to 0 and 10. And that's sort of true in the sense that you might have stopped executing your software when, according to our model, A pointed to 0 and 10. And the second step is some kind of a recovery plan. We'll talk more about recovery in a bit, but the sort of salient point for modeling the disk is that on reboot, you're going to choose one block value for each address. So for this address A, we're going to choose one of these values, either 0 or 10, and so on for every other address. And the interesting thing that this captures is that when you crash, you lose the disk buffer, and you're not allowed to get it back again. So it would be weird if, for example, you had a write buffer, you had a bunch of outstanding writes, like the 0 and 10. Then you crashed and rebooted, and then your disk said you read address A, you got 10 back. You didn't write anything, you crashed again, now you get 0 back when you read it. That's not allowed. You can't sort of keep around all these different values for a long time. As soon as you crash, you have to collapse to a single value according to this model of rebooting and recovery, and then you're not allowed to sort of change from that value you've chosen after a crash. That makes sense in terms of how do we reason about execution of code here with crashes?
Actually, if the disk is fairly independent of the CPU, you could imagine that the CPU might crash and restart, and the disk might still be buffering the stuff.
Yeah, so that would be indeed a way to violate our model, is that That's right. Like if you lost power and your CPU was pretty power hungry, so it rebooted right away, but the disk had a capacitor and kept running, that would be a violation of our plan, indeed. And these kinds of partial failures are really tricky to deal with in distributed systems where this happens for maybe more legitimate reasons, where one computer reboots, the other one doesn't. But indeed, you might think of a single computer even as a distributed system with the disk versus CPU.
You might think that it would be a good idea to explicitly do some kind of sync.
Yeah,
as
I
part of a
wonder what
reboot.
happens here. So there's, I don't, it's been a while since I read the Atapi spec for SATA. I don't recall a command to discard disk buffers, but maybe there's some kind of a general reset command that in practice will achieve this result.
Isn't there a sync command?
There's a sync command, but I don't think any OS runs sync just for the heck of it on boot up.
Really? Gosh, I think that would be a no-brainer.
Interesting. Yeah, maybe like I think Linux is very parsimonious with issuing syncs, and yeah.
Well, but a crash is pretty expensive.
That's true. Yeah. So I don't know. Maybe I should double check. I should say I haven't looked very carefully, but I've looked at some traces of Linux booting up, and I didn't see any syncs issued. All right. So one other thing I want to talk about next is, so we've talked about low-level modeling of the disk and how we're going to reason about execution of code. So let's now talk about how we're going to actually specify logging on top of our disk model. So here I have a simple example from the paper where we're trying to write two things to the disk atomically using the write-ahead log. And just to explain this extremely concretely, what the disk has is it's got a log and some disk location. So this portion, let's say, is going to be reserved for the log, and these guys are actually the sort of installed or applied values. So the way this logging is going to happen is that first you're going to write this address and value that you want to write into some location in the log, and then you keep writing them, and you fill them up, and then when commit happens, it actually writes here to the header the number of blocks that you want to commit to. And once this write happens, commit internally is going to call sync, and then apply them, which means taking the V1 from this log and putting it at this location A1, and then this location A2, installing that value. So that's what this code is actually doing. So the question is, what is the more abstract way of thinking? How do we capture this notion that this log abstraction is going to make our writes atomic? So the idea here is to, again, come up with an abstract state for what the logging system is providing to us. And the way that FSCQ proposes thinking about the write-ahead logging system is in terms of these logical disks. And these logical disks, what they're meant to represent is sort of this range of the disk. That's maybe the wrong color. Let me make this yellow. So this is the range of the disk that FSCQ is trying to describe with its logical disks, because strictly speaking, these are the only addresses that the file system should be using on its own, and the logging system owns this left portion. These logical disks represent this sort of yellow region. I guess in my example, it ended up being 3 blocks. But the interesting thing is that in the abstraction provided by the logging system, these guys are not just sort of truncated to the installed region here, but they're also synchronous. So this is back to the simplified model I showed you guys earlier on, where every block in this logical model has a single value. So here's like V0, V1, V2, and V0, V1, V3 maybe. So these are different logical disks. And the way that we're going to phrase the spec of the logging system is that the state of the logging system is always consisting of these 2 disks. One of them is going to be called the committed disk, and the other is going to be the active disk. So the rules of the game are, or what I mean by rules of the game is, the way we're going to describe the spec of the system is by saying that operations like log read and log write, so log write, for example, is this thing that our example is calling on the left. These guys are just going to operate on this synchronous disk called the active logical disk. And these guys look exactly like the specs I showed earlier for the synchronous disk, which turned out to be too simplistic for reality because it didn't capture asynchrony. But it turns out it's actually perfectly great for describing the operations of reads and writes on this active disk in a transaction. And then what happens is now we have to describe commit and crashes and recovery. And here's the cool thing. The way to think of commit is that commit just copies the contents of the active disk to the committed disk. So for example, here, the active disk has the value v3 here. So what commit is going to do is it's going to not change these guys because they're equal, but it's going to change v2 to now be v3. So that's what commit does. And then the other thing I need to describe is what happens on crash. So if you crash, then according to this model of the logging system, this is what happens on recovery. So if you crash and recover, then you just copy the committed disk back to the active disk. So the reason this nicely captures our atomicity property is that you can think of the committed disk as the only guy that actually kind of matters for durability purposes, because on crash, we're going to throw away the active disk and completely overwrite it with whatever was in the committed disk. And the cool thing is that you can read and write all you want to this active disk, treat it like a synchronous disk, but all that's going on is that you're actually sort of building up some stuff in memory. And when you call commit at the spec level, as a single operation, you just replace the entire disk with all the changes that you've built up. So that captures the fact that all of them are going to happen at once, and you don't have to worry about individual writes leaking out. So does that make sense as a way of modeling what a logging system does? Any questions about this? So it's pretty cool in some way, because we're basically getting back a very nice model of a disk that looks just like memory. There's no funny lists of values that we were seeing for our asynchronous disk. And we get the only sort of changes, instead of just doing reads and writes, you got to call commit at the end of the day, or at the end of your system call, to make these changes persist. All right. So the other thing I wanted to touch on here is how the logging implementation in FSCQ actually connects this abstract state to the concrete state. So if you remember from your labs and from all the lectures, there's always an abstraction relation that's needed. If you have an abstract state, we have this logical view of stuff in terms of these two disks. But what does it have to do with reality? Well, this is the log rep predicate that FSCQ has. This is a log rep predicate from the paper. So this log rep is basically a separation logic predicate that takes the logical state, this is the abstract state, up here being passed as arguments to log rep, and this predicate then applies under the covers to the actual full disk. And this has asynchrony on it. So here's what this predicate is telling us. So there's actually another thing here, which is like a type of state. And what I mean by this is that the logging system can be in many states. The state in which it's in for the most part of the time is this active transaction state, meaning that the application, the file system, is running and doing some changes. And then there's other states that we'll look at in a second. But for the most part, this active transaction state is going to describe what's on disk when you're in this logical state, where you have a committed state, here called the start state, and this active state here called the current state. So this predicate says that, well, there's the commit header, which is this guy over here. This is the commit block. And this says that the commit has to have the value 0. And this empty set basically says there's nothing else. The list is only 0. That's the only element in the list. So that basically says that there are no pending writes to commit block. We've flushed everything. And this is the separation logic star. It also says that there's some other addresses in the disk. And what those are is basically all the contents of the start state, which is the committed state. So we say that for everything in the committed state, all those values are currently stored on disk with this points to relation, and their value is present there, and there's no outstanding writes to them. So what this invariant is saying is it's sort of covering this region of the disk and says that there's no 0 and no outstanding writes, and it covers this other region as well. And this empty symbol indicates that everything here is flushed, and everything in this log header is also flushed. This is a very strict requirement on the contents of these guys. It doesn't actually say anything about the log region at all. And the reason it doesn't say anything about the log region is because in the log region, it doesn't matter because we say that the length of the log is 0 in the commit block. So those guys are unused. And then what we say about the active state is, well, actually, all the active state is it's logically what you would get if you start from the committed state and you apply all the values that we've been tracking in memory. So this is exposing another part of the implementation, which is that the logging system maintains an in-memory queue of writes. When you issue these log writes, these guys go into some kind of an in-memory log that's not committed yet, and this abstraction relation describes how this in-memory log connects to the active state that you logically see in the spec. That make sense? Any questions about this so far? All right. So now let's talk about how we actually prove some piece of code on top of this logging system. And the thing I want to talk about is really recovery and how we're going to sort of prove this. So the interesting story for FSCQ has to do with how we extend HOR logic for reasoning about code like this recovery procedure, perhaps. So the rules, if you remember, for HOR logic is that you have pre and post conditions for all your little pieces of code. So here, for example, the first thing we do is log read is just a read. So we already have a pre and post condition for a read. And then we're going to do read log, and then maybe other operations and so on. And if you recall, with HOR logic, the plan is you look at the overall procedure that you're trying to prove here. So this overall procedure here is this recovery function. And we take its precondition and we prove that this precondition implies the precondition of the first read. Then after we're done with the read, we prove that its postcondition implies the precondition of the next thing, and so on and so forth until we prove the postcondition of the whole recovery. So this is the step proc tactic that you guys are using in the lab assignments. It basically does the same sort of chaining. The one difference is that in FSCQ, we got to reason about all the possible points at which we can crash. And this is handled by a crash condition, which I'll sort of, in this picture semantics, I'll draw at the bottom of these little boxes representing the HOR logic spec for each piece. And the rule is that basically at every step, you chain forward the pre and post conditions, which that reflects the sequential execution if everything goes fine. But at every step, you also have to prove that the crash condition of each step is part of the crash condition for the whole procedure. The way to think of this is that you're proving that the crash condition of the entire recovery procedure here is the or, it's the union of all the crash conditions of all the individual pieces along the way. So you're carefully tracking all the ways, all the places where you might crash in running this procedure. Does that make sense? This is sort of the extension to HOR logic that the paper calls crash HOR logic, because it sort of adds this crash condition and helps us reason about that. Any questions on this crash reasoning here? Maybe the last thing I'll sort of show you guys before wrapping up is this spec for log recovery. So this is a really cool property that's worth knowing about called idempotence. It turns out to be really important for crash recovery systems. And this is a spec from the paper for the log recovery procedure. We just looked at sort of code on the previous slide. The cool thing going on here is that this recovery procedure has a precondition that here is this log intact thing. And this basically describes all the states in which you might crash, where here's your committed state, and here, here's the last state in which you were, and here's the maybe the new committed state that you were just in the middle of committing. So there's maybe uncertainty as to where you're going to crash exactly. And the way this recovery procedure is going to get used is that your application running on top of the file system has all kinds of crash states of its own. And in order to make sure that your application and file system is going to be recoverable, you have to prove that all your crash conditions while your file system is running imply the precondition of recovery, because this recovery is always going to run if you crash, no matter what. Can't depend on what application code you are running. And if that happens, then your crash condition implies that it's actually safe to run log recover after a crash. And the post condition establishes that either the last state is there or the next thing you committed is there. So basically, either you have one state, sort of one logical disk, or another logical disk, but you're no longer in this, I don't know, some kind of superposition of logical disks represented by this log intact thing. And here's the cool thing. The crash condition for log recovery is actually the same as its precondition. So this log intact thing, in the crash condition, what that is capturing is the fact that if we crash during log recovery, we're going to run log recovery again. But because the crash condition here trivially implies the precondition, that's totally safe. So we can actually keep crashing during log recovery as often as we want. We can crash one time, 100 times at different points. We'll always re-enter log recovery, and it'll always just keep working until eventually we stop crashing. We're going to pop out with one logical disk or the other. So this notion of idempotence captures this essence that it's safe to keep running this log recovery many times, in this case, including if log recovery keeps crashing, and we'll still get the same outcome, one of these two logical disks. That make sense? Any questions at this end of the lecture? All right, so that's all I have to say about FSCQ. This is a sort of exciting paper for us because this is what got us into verification in the first place. There's lots more sort of to come, so we'll talk about other systems going on, and in particular, next week we're going to start talking about concurrency, which is a big topic for figuring out what the right spec is and how to do proofs. And it's a tricky issue that the papers we've looked at so far have mostly ignored, though. So see you guys on Tuesday. We'll talk about memory models then.